All right, today we get to talk about measuring complexity. This comes from chapter 5 of software measurement and estimation. And we'll get started on that. Looking forward, the next week split over March, we're going to be covering the first two sections of chapter 6 next time. So we're going to split up chapter 6 and we'll cover it the next week. Okay. All right, so measuring complexity. So we've talked about measuring size. Now we're going to talk about measuring complexity. And the goal here is to reduce complexity. Okay, and some of that we just can't do because it's a software project and we have to do what you have to do. But some of the benefits that we can derive from this is we can have reduced development defects. Reduced development and maintenance cost. Okay, so we're talking about companies. Companies deal with dollars, and so we want to be able to do this. And so understanding these concepts will help us to be able to redo that. And what we're going to do is we're going to use complexity to predict defects and productivity. Okay. Also, defect proneness, so how likely it is to have a defect, and productivity are so what we're going to do is we're going to use those as the operational definition of complexity. What do I mean by that? I mean, okay, well, how do we quantify complexity? One way is how prone is code to have defects and how productive are we? Okay, so complexity is a little harder to put our hands around, but yet we can we can measure defects and we can measure productivity. Okay. Who's heard of the KISS principle? Valentine's Day was recently. Might apply, might not. KISS principle. What does that have to do with this? So KISS is K-I-S-S, right? So what it is keep it. Have you heard of this? Simple, stupid. Okay, and this is attributed to Kelly Johnson. He was a lead engineer at the very prestigious Lockheed Skunk Works. This is about 1960. Good year, yeah, good year. And so this is not to make fun of engineers, but more of the opposite. And so what they did was they were building secret fighter jets and things like that like Blackbird. And so, but even though they're building these, pushing the limits of technology and science at that time, the principle was keep it simple. Okay, we're doing some complex things in other areas, so as much as possible, keep it simple. Okay, and so that definitely plays into software. If you can, as much as you can, keep it simple. Simple is beautiful. Okay. There's three aspects of complexity that we're going to talk about today. The first one is structural complexity. The next, and we're going to spend most of our time on structural complexity. And then we're going to talk about conceptual complexity, and then we're going to talk about computational complexity. Okay? So, first, structural complexity. That's not what I want. There we go. All right, so what is this? This is the design and structure of the software itself. Okay? We're talking about, okay, well, what does the software look like? we're going to be measuring that. So as background, let's talk about a few software engineering concepts. Who's already had software engineering as a class? Okay, so before class next time, just study up on the entire undergraduate semester of software engineering and get back to me. Okay, so we'll cover a couple things, okay? Coupling, okay? What is coupling? Anybody work with pipes? A coupling for a pipe takes one to another. So the concept is we're joining something. You can say, oh, look at that cute couple walking down the hallway. Well, that's two people that you are joined together, okay? So coupling in software is the strength of the connections between modules in a system, okay? So we're talking about modules and how coupled are they in between, okay? So here we say the higher interdependent. So inter meaning in between, okay? Intra is internal, inter is in between. Interdependent systems mean higher, or here in this terminology we say tighter coupling, okay? So if there's two modules and they're highly connected between each other, they're tightly coupled, they have a high coupling, okay? With tight coupling, changes to one module, what is that? How's that going to affect the other module if they're tightly coupled? They'll probably affect the other one. To continue our analogy of a human couple, we have if you have two people that are highly interconnected, if one is having a bad day, what's that going to probably lead to? Human nature. And so that helps our intuition for what does coupling mean in software, okay? So good design has what in terms of coupling? High or low coupling for good design?
So if one gets affected, the other will also. So both are dependent of each other, right?
So when you have high coupling, you make one change over here, and it's probably gonna.
So low coupling for a good design, low coupling.
Low coupling, and what we do is we call that loose coupling. Now that's not good for relationships, but if you talk about, well, if one person changes, it doesn't affect the other person, well, that means they're not very connected. Someone you see once a year, they're having a bad day, probably won't affect you in general, okay? To continue with that analogy. Okay, so that's coupling. Now let's talk about cohesion, okay? Cohesion. Let's just pull up the dictionary definition of this in English. Cohesion in my dictionary says the act, it says, it doesn't say anything. Cohesion, where'd it go? Oh, now it's at the top. The act or fact of forming a united whole, okay? So we're trying to, cohesion is we're trying to bring something together. That's what it means in English. Now let's talk about what it means in software. In software, it means how strongly the elements are connected within each module, okay? So the coupling is between two modules. Cohesion is within a module, okay? So is everything nice and well connected, or is it kind of loose spaghetti and you're not really quite sure what's going on inside there, okay? So good design has what for cohesion? It's going to have tight cohesion. Okay, so you want your module to be the elements within the module to be tight, but then the modules be loosely connected in between. Okay, so those are some good design principles. Okay, so now let's talk about structural complexity metrics. Okay, so how would we measure structural complexity then? What would come to mind if you were going to measure this? Well, you might think, okay, well, what's easy to measure? Size is going to be easy to measure, so we'll talk about that. Another one we're going to talk about is cyclomatic complexity, okay? And that measures the control flow within a module. We'll talk about Halstead's complexity, okay? That's the number of operators and operands. We'll talk about information flow, which looks at the number of flow of data into and out of modules. We're also going to look at system complexity. Some examples of this are maintainability index and the Agresti card glass metric, which we're not going to cover. And then we have object-oriented structural metrics, okay, which are specifically designed for object-oriented programs. Okay, so let's look at each of these in turn. Okay, so size. How do we measure size? Say what?
Using any scale.
Any scale? So this is chapter 4 topic. How do we talk about measuring size? There's lines of code. Do you see a theme here in this class? Okay, lines of code, lines of code, lines of code. So on the final, a good way to measure software is lines of code. Or maybe more aptly put, the most common way to measure software is lines of code, partly because once you have that definition, bam, I mean, you could write a parser today that would go through and count lines of code. I could do it in 2 seconds if we're having a really loose definition of count everything, right? You just say, hey, count all the lines in this file. That's a Unix command, bam, done. We're good. Okay. So lines of code. There was another way we talked about last chapter. What was the other way? We said, okay, well, what about block programming or visual programming methods? Like lines of code doesn't mean anything. So what are we going to do? We needed something, and the clients are more interested in what than lines of code? Does that help? Function points, okay? Function points. Now, if you're going to use function points, then they're converted to lines of code using the language's gearing factor. Okay, so if you'd rather use function points, that's fine. But then we say, okay, well, what's the equivalent lines of code for that? Okay, so that's how we measure size. And so the common reasoning, as I'll call it, is that the bigger something is, let me spell correctly, the more complex it is. Okay, so now most effort estimation models, and we're going to talk about effort next week more formally. Most effort estimation models use lines of code as the primary factor, okay? So you're starting to see this motif. Wow, that really comes up a lot. Well, partly because it's simple, we can agree on it, and it works just as well as about everything else, so why not use it? Okay, so there's some trends we need to wrap our heads around. As size increases, what happens to complexity?
Increases.
It increases, okay? So if I said, if you think back about the projects you've written, think about the 100 lines of code projects, the 1,000 lines of code projects, the 10,000 lines of code projects. As the number of lines go up, I mean, sometimes it's just more of the same features, but just the fact that even you went from 5 features to 10, there's a little bit more complexity there.
Even if we write 100 lines code in one line.
Oh, in general. Yeah, we can come up with like this one line of code calculates the International Space Station's position relative to Mount Everest. Okay, that could be one crazy line of code. Do you know what I mean? But so that's a counterexample. But in general, right? This is used and works for estimating and predicting things. Okay. Now, part of it is if you are NASA or your government's space exploration program or whatever, your calibration, your coefficients for these things are going to be different. And so you need to know for your organization how to apply these, okay? Because if you're a kid software company, that's different than if you're a financial software company giving financial advice. It's different if you're handling financial transactions. It's different if you're a real-time embedded mobile device company. It's different if you're doing life support software. And so these are all different, and they're going to have different lines of code and how fast you produce them and tolerances and things like that. Great discussion. Thank you. Other points? Okay, so as software increases, what about defects? It'd be nice if they didn't, but then that'd also be awkward. Oh, I need to make the code bigger so that I have less defects. No, I mean, the more code you write, the more defects you're going to be. The more I type, the more words I misspell. Some of which I catch, some of which I catch before I post these notes. Okay, so as size increases, defects increase. Okay. What about this one? As size increases, defects density, which is then defects per line of code, what happens to it? Increases, decreases, or remains constant? So the how dense they are is a debated topic. Okay, the authors of our textbook emphatically argue that the defect density remains constant, and that so as your size increases, the number of defects increase, but not. It's because there's more code, not because there's more code and there's more complexity, which to me is a little bit counterintuitive. I would think that the number of bugs that get in a code as it gets more and more complex are going to be more and more bugs, more and more defects. And so to try and figure out, but they say, hey, actually, they argue that the data shows that as the size increases, the defects increase, but linear to the size and not super linear. And so they remain constant. Now, but that's debated. So you'll run into people that'll say, oh, blah, 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 blah. You know, that's wrong. That doesn't apply here. Interestingly enough, you can look at what should be the size of a module. How big should a module be? And you can look at it in terms of defects. And studies have shown that the size of a module should be about somewhere between 400, maybe as low as 200 to 750 lines of code. Okay, and one thought is well, this correlates with how much we can keep in our head. If it's too much to really keep in our head, then we're going to miss things. We're not going to understand things. And so beyond that, it gets too much to kind of keep in our minds of everything that's going on. But you can look in the textbook for more information on that. Okay, so that's size. Okay, now let's talk about the structural complexity metric, cyclomatic complexity. This is abbreviated CC. So this is the most famous and popular of the complexity metrics, holding size in its own category. And what it is it's the number of control flows within a module. Okay? So how many control flows there are within a module. Now, intuition is that as the paths through a module increase, as the path through a module increase, the complexity increases. Okay, so initially this was developed for how testable and understandable is a module. Okay, so we'd like to know for this module, are we going to be able to test it easily or not? Do we predict that we're going to be able to understand it well or not? And so that was initially the concept. What it is it's based on classical graph theory. And specifically the cyclomatic number of a graph. Anybody come across that before in graph theory? That's fine. Okay, and so this is V of G. Okay, and what this is for those in the back that haven't had it before, the number of linearly independent paths within a program. Okay, so let's continue to look at this. So the number of linearly independent paths through a program. How many paths are there through a program? Thought of differently, it's the number of scenarios that need to be tested. Have you anybody covered software testing formally in a class? Okay, so each branch needs to be tested. Okay, because if it doesn't work, I mean, what is unfortunately all too common with students is, I ran it once, it works, I turn it in. It's like, well, I believe that. I believe that it worked one time. It looks like it compiles, but I have 3 test cases and they failed 2 of them, or they failed all 3. Well, I didn't test for that. Well, that's per the specification. So that's all too common for a student, someone learning to do. That's not acceptable in industry. Oh, boss, I tested it once. I'm really surprised the customer found a bug. It's like, whoa, wait, you tested it once? No, you need to test one test for every branch. And so that gets at all the different paths that come up. The number of, okay. So the cyclomatic number can be calculated in 2 different ways. We have V of G equals E minus N plus 2 and I'll define these terms in just a second, and equals b times d plus 1. Okay, so now what are all these variables? Well, g is the control graph. We'll talk about that in a second, of a module. Okay, so it has a starting point and an ending point. E is the number of edges. What do you think n is? Number of nodes, because we're talking about a graph. BD is, the product is the number of binary decisions in a control graph. Okay, so let's look at these. Okay, so let's cover some basics here. What is the blue circle? Is it an edge or a node?
No.
It's a node, then the arrows are edges, okay? Aha. Labeled here. So we have nodes and edges, okay? Just to make sure we're all on the same track, because this isn't a graph class, but I hope you've come across that before, okay? And so now let's talk more about control graphs, okay? So here we have three control structures. Total, not in order, we have if-else, a sequence, and a while. Which one is which? Which one's the sequence? Which one's the if-else? Which one's the while? Sequence is the first one, right? We just have one line of code, we have another line of code, or we have one block of code, it goes directly to another block of code.
The second one sequence.
This is the if-else, okay? And then this is a while. Can I vote?
No,
While is the second one.
While is the second one.
Yeah, it repeats.
Okay, right? Because we come here, we come back here. We come here, we come back here. Oh, we're done? Okay, then so that this is a while loop, a loop, okay? And then here it's two roads diverge in the yellow wood, and I took the one less traveled by, and that has made all the different sense. It's a American or English poet, Robert Frost. Okay, I didn't just make that up. And then we come back together afterwards, both paths come back here. Okay, so that gets back at the basics of structures. Okay, so sequence, while, and if-else. Okay. Okay, so now let's calculate the cyclomatic complexity for each of these graphs. Okay. Okay, so the cyclomatic complexity here for sequence. We've got two ways to calculate it. Let's just do both. So what's the total number of edges for a sequence? 1. What's the total number of nodes? 2. So 1 minus 2 is minus 1 plus 2 is 1. So it has a CC, a cyclomatic complexity of 1. Okay. Look, let's calculate the other way. How many binary decisions are there here? There's 0. So there's no forks, there's no branches. Okay, so BD is 0. So 0 plus 1 is 1. Good. They should both match. If they don't, you've done something wrong. Okay? Okay, let's look at the while here. Number of edges is 1, 2, 3. Number of nodes is
3.
Okay, so 3 minus 3 plus 2 is 2. How many binary decisions do we have here? How many times is there an out degree greater than 1? Right here, we have to decide, do we go to this node or are we done and we go to this node? So there's one binary decision. If you're here, there's no decision, you come back here. The only decision is at this node. Okay? And so the BD here is 1, so 1 plus 1 is 2. Great. Okay, number of edges, 4. Number of nodes, 4 minus 4 plus 2 is 2. How many binary decisions do we have here? Just one? We have 1. Okay, because this one has an out degree of 2, out degree 1, out degree 1. Okay, so this is the only one where we have the decision, right? We go to the if, and we go to the else, or vice versa, and then we come together. So then 1 plus 1 is 2, which matched up with what we got before. Okay, great. Okay. Well, no, those are control graphs. Now, let's go back to string cat that we covered before. Okay, let's apply to some code. So this is what we looked at before. Okay, this is from, was it from Apple? Yes, this is from Apple. So what is this cyclomatic number for string n cat? Okay, so let me just pause the video, and I'm going to float around and work on that, and then we'll come together, okay? So there's no graph here, so the other option is looking at the binary decisions. How many binary decisions are there in string n cat?
4.
What was your vote? 4. Okay. Okay, where are they? If is 1, right? We may or may not come in and do anything. Okay. 2. And so we go through this loop to count things up. Okay. Oh, so, okay, so 1, 2. We have another if. And then we have a do while, which a do while in C and other languages is you do it once and then you decide. But you still have this decision, am I going to keep doing this or am I done? So we have two ifs, 1 while, and 1 do while, each of which are decisions. Okay, and we could draw this complex graph. Okay, so that was 4 binary decisions, so 4 plus 1 is 5. Okay, so this has a cyclomatic complexity of 5. Okay. Questions on that? Could you take other code and calculate the cyclomatic complexity of it? Or look at a graph? Okay. All right, so as the cyclomatic number increases, we expect the complexity to increase, and that the module is harder. Remember, this was talking about testability at first. Harder to test and to maintain. Okay? The more branches you have in there, the more test cases you need to come up with to make sure that you've tested everything appropriately. So NASA has in-house rules of, hey, if it has a cyclomatic complexity above this, we probably need to split up the routine, or we need to be more careful of it. There's some engineering rules behind this, as you know, 20 is really high, 50 is like, really? You really are gonna, use this code? You better have a good justification for why. Okay, so the way to use cyclomatic complexity is where it's appropriate is to identify modules that needing increased design review. Okay, so I'm not saying like, oh, this is a bad module. It might just be like, look, that's what it is. You know, inherent in this program is all this structure. Oh, okay, well, that is what it is. Or could we design this better? Often it's going to be, oh yeah, we could design better. The other way to use these is to estimate maintenance effort and testing effort. Okay, so we talked lines of code, lines of code, lines of code, but now okay, here this will be great to give insight into predicting maintenance effort and testing effort. Okay, so I would suggest you combine them. So there's many tools that exist, including freeware, to be able to do this. Okay. Questions on cyclomatic complexity? Okay. So let's look at another structural complexity metrics, the Halstead's complexity. So here, as I mentioned before, it's the number of operators and operands. Okay. And Halstead came up with what he calls software science. Okay. And here's the software science. We have, well, let me just define these first. So n sub 1 equals the number of distinct operators. Okay, what's an operator? Math operators and increment, etc. Okay, number of distinct operators. N sub 2, because you can't use n sub o because the other one is number of distinct operands. Okay, what's an operand? Something that an operator acts on in general. Now, these definitions don't quite match up with what we'd probably teach in a computer science 1 class. Capital N sub 1, so this is lowercase, lowercase, capital, is the total number of operators. N sub 2 is the total number of, you guessed it, operands. Okay. Now we have this software science here where we have the length is the total number of just everything, operands and operators. Okay. The vocabulary, as Halstead defined it, is how unique is it, right? So a vocabulary is, well, how many words do you know? What's the total unique words? Not can you say the same word over and over and over again. That would be length, whereas vocabulary is how many different words do you have at your command? If you are learning a different language, you feel this very poignantly. And I'd say, oh, poignant, that's a word I don't know in English yet. But because you're limited in your vocabulary in the second language, especially compared to the first language. And as that increases, you feel more and more comfortable. And you're able to speak more fluently and comprehend more fluently in that other language. I'm fluent in a different language, and I can't imagine taking a university class in another language. Oh my goodness. So partly it is I've never learned the technical terms in Portuguese. So yeah. So that'd be challenging, difficult, arduous, strenuous. What other fancy words? Okay. So there's some other metrics he came up with. You know, 2's just not enough, isn't there? So he said, well, volume. Volume is n times log base 2 of n. Okay, so what's the vocabulary, the log base 2 of the vocabulary times the length. That's the volume of what we're talking about. He also talked about the difficulty, or D, where D is n sub 1 divided by 2 times n sub 2 divided by n sub 2. N sub lowercase n sub 1 divided by 2 times uppercase n divided by 2 divided by lowercase n divided by 2. And then effort has been defined in multiple ways. Here it's going to be defined as D times V. Okay, the difficulty times the volume. Okay. All right, time for another exercise. So the exercise is to calculate these metrics, again, for our favorite string and cat. Okay. So how do we do this?
What is the difference between distinct operators and total number of operators?
Okay, so the word distinct, thank you for asking. The word distinct means, so let me pull it up this time. What? Oh, okay. Distinct, different from something else of a similar type, okay? There are 4 distinct people in this room, okay? Each one of us is different. Hold on. That was a bad example. I have in my hand 3 black markers and 1 blue marker. There are 2 colors. There are 2 distinct colors, total of 4. So the thing is, if an occurrence is repeated,
This is not to be counted.
it's not to be counted. Okay. My analogy with humans was bad because each human's unique, didn't it? Okay, so distinct operators. What are our operators here?
Logical operators.
How many do we have?
4. 4 distinct
So the way the book counts it was curly braces as a set is an operator. Not equal to is an operator. We have an assignment as an operator. We have equality as an operator. Inequality, 5. We have increment,
Decrement.
6. Decrement, 7. We have dereferencing, 8. Now they came up with 11. I'm trying to think, how did they, what were the other 3 that they came up with? Semicolon was one of them. Okay, the semicolon there. But you only count it once for distinct. Okay. So we're at 9. There's 2 more. Comma, I think, is one of them. And then we're missing 1. Dereference, increment, semicolon, inequality, dereference. wonder if parentheses.
Parents, yeah, full study helps.
Good job. Okay, grade plus plus. Okay. Okay, so that's N sub 1. Do you see how some software to calculate these things would be really good? Like manually, it's a pain, but that's fine. You can write a computer program to do that. And then you don't make mistakes, and it's very repeatable. Okay, so that's N sub 1. Okay. Now let's go on to the next one. N sub 2. So that, I'm sorry. The book has the code a little differently. It doesn't have registers in there. I don't know that it even has const, and it only has while instead of do while. I mean, right, there's more than one way to write it. But they came up with, in the book, they came up with 6 distinct operands, okay? So if we used n sub 1 equals 11 and we use n sub 2 equals 6, their total count, and their code is a little bit different than the one here, is n sub 1 is 26 and n sub 2 is 10 different operands. Okay? And so then we have length equals, the length is the addition of those two, so length equals 36. The vocabulary, how many distinct things are there? In the textbook example is 17, because that's the number of distinct, right? Because if you basically did the code twice, vocabulary is the same, the length is longer. The volume here, if you calculate that out, or if you're really good with log base 2, is 147. The difficulty here is going to be 9.2. And then the effort is 1348. Okay? So what I'd probably do on a quiz would be to have this be one set of questions and then this be a second, because this, the second set, the metrics are all based off these values on how to be able to calculate them. So these would be good to know, how to calculate the length, the vocabulary, the volume, the difficulty, well, the effort, but to know the effort, you need to know the difficulty and volume as well. Okay, so what's the major disadvantage then of Halstead's complexity? So what has to be done before we can calculate Halstead's complexity? So the disadvantage is that the code must be written. Okay, so if it must be written, then there's no predictive power for development. Okay, so because development is over, or it's very much underway, but what it does do is it does provide us a predictor for maintenance effort. Okay, so that's where its strength is, and so maybe as you're concluding development and you're looking forward to maintenance, then you can apply Halstead's complexity, but you can't do it at the beginning. Okay, so that's something to keep in mind. Questions on this? Okay, let's move to another structural complexity metric, information flow. So here, this is a measure. It measures the information flow into and out of modules. Oh, hold on. We skipped an exercise. We'll come back to it at the end. Okay. Okay, it measures the information flow into and out of modules. As information flow increases, complexity increases. Okay? So as the information flow increases, it's just you've got more coming in and going out. It's more complex software. Okay, so this is proposed by Henry and Cafferat in 1981, and what they proposed was an information flow complexity, or IFC. Okay, to be formal about it. And so we have a logical flow if procedure A calls procedure B, okay? If B calls A and A returns a value to B that is used by B, and both A and B are called by another procedure that passes a value from A to B. Okay, now they define fan-in as the local flows defined above into a procedure summed with the number of data structures from which the procedure retrieves data. So fan-in is what is coming in, flows into procedure plus the number of data structures. Fan-out is the logical flows from a procedure, not surprisingly, plus the number of data structures the procedure updates. Okay, so which ones is it using? Which ones is it using in a read-only manner? Which ones is it updating, changing, setting, populating? Okay, here length is defined as the number of source statements in a procedure. And this here, it's explicit that it excludes comments. Okay, and so now we have the definition for information flow complexity is fan-in times fan-out squared. IFC is fan-in times fan-out, that product squared. Similarly, we have weighted IFC, as you could probably guess, is length times IFC, or fan-in times fan-out squared. Okay, you guessed it. Let's apply it to, there it is, our favorite string end cat. Let's see if I can move this down. Hey, nope. That should work. Okay, we're talking about flows into and flows out of. What's flowing in here? That's a great point. It's kind of not well defined for a module. So let's ignore that component right now for the fan-in. Okay, and let's strictly look at the data structures. How many data structures are coming in? Well, we have 3 parameters here. 1, 2, 3. So then we'd say there are 3 data structures coming in. Okay. So now let's look at fan out. Does it call any other routines? Nope. Short and sweet. But does it update any data structures? The data structures that it's updating is this destination because we return it. Okay, so this is read only, this is read only, this is read and write. Okay, so destination here for string incat is read and write. Okay, okay, so let's write down these values. Now we have fan in equals, we said I don't know plus 3, so we're going to call that 3 to make it calculatable. We had 0 plus 1, which equals 1. We have the length. We said before it was the one in the textbook is 10 lines. This one's a little bit longer. So now we have IFC is fan in times fan out. So 3 times 1, that product squared. So that equals 9. Okay. And then weighted is 10 times 9 equals 90. Okay, so then you have this complexity here, but then how much is it? How much is it stretched out? Is it very complex but very short? That would be back to the equation for, from Mount Everest to the space station. You know, that might be short, super complex but short. And so that's what this is getting at. Okay? Questions on this? These equations at least a little easier to wrap our heads around. Alternatively, the information could be given in a graph, you know, because then a graph has in degree. Are you familiar with in degree for graph nodes? How many connections are coming in? Out degree is how many connections are going out. So fan in would then be the in degree, and then the fan out is out degree is basically what we're looking at. Okay, we've only got a few more minutes. Let's hit the highlights for structural complexity metric system complexity. Okay. Let's just talk about the maintainability index here. So this is MI, and this one's awesome. This is not one that I'm going to expect you to memorize because it's just this crazy collaboration between University of Idaho and HP where they came up with this. They came up with this equation, and it's hard to type and talk. And then what got me the most was there's sign in here. It's like, what? There's sign in here. Now you got to be careful how you use sign, or it's going to oscillate up and down. Square root. Okay, so as you probably guessed, these constants were derived from data, and so they had a model. They applied that model, and then they applied the constants. They empirically derived all these constants here. So here we have AV is the average Halstead volume, or V, that we talked about before. So it's average per module. Okay, AV of G prime equals the average extended cyclomatic complexity, again, per module. ALC, as you probably guessed, was average count of lines of code per module. Okay, and then the per CM equals the average percent of lines of comments per module. Now, if you felt like comments were dissed earlier, then here's the redemption. Here's where they actually play into a metric explicitly to the system complexity. Now, notice that sign there. And so while it says percent, the range for this needs to be, you need to use the ratio, or it needs to be between 0 and 1. Otherwise, you're going to have this oscillating behavior, which is just kind of crazy. So it's the ratio, and then that way it's just a small part of the sine curve. It just increases. So here, let's just look at this equation. Okay, we have this crazy constant, 171. We have minus the average volume, minus the average CC, minus the average lines, the average LOC, plus some the comments. So as the comments increase, what happens to this? Our maintainability index. What would you assume? If we're looking at maintenance and we're trying to study the effects of comments on that. More comments, less comments, what would you expect for the maintainability index? The more comments, the better. To a diminishing return, if you graph it out, I mean, once it hits about 70% of your code is comments, that's crazy. You know, good, a lot of documentation. I've had code where I've spelled out, this is the 4 examples, let me illustrate it graphically for this overlap, and I felt like that code was, that part was easy to maintain. It was more comments than others, but usually I write more code than comments. Now maybe I need to repent and change my ways, but so as it gets close to about 70%, there's very little extra value for having more comments, okay? But if the code was entirely comments, then that would be the maximum value. So it's kind of like we have this value and we only lose maintainability as the volume increases, as the cyclomatic complexity increases, as the modules get larger overall, with the only redemption of what percentage are the comments here, okay? So then here, as the maintainability index increases, then this is maintainability increases, as the name of the metric suggests, okay? We are short on time, so let me say object-oriented code is different than procedural code, okay? We have classes. The classes hold the data. Classes act on their data. So they're fundamentally different. Because of that, it requires different metrics to be able to look at the complexity and apply to that, okay? So that concludes structural complexity. Let's just spend a moment on conceptual complexity. So this is more psychological. This is how hard is the software to understand. There's not a lot of hard metrics on here. I'm not going to present any because how do you gauge that? How do you say, well, this is hard to understand? Well, might be hard for you, might be easy for you, and vice versa. You might say, oh man, I love a good recursive function. It takes me a moment, but once I've got it, I've got it. It's so much better than an iterative one. And somebody else might say, oh, just the word recursion hurts my head. You know, like just the thought of it makes my head hurt. Okay? So this is very difficult to measure, but it needs to be accounted for in design. Okay? So it's something to keep in mind, but it's not like you're going to report it on some scale. So computational complexity is how many resources are used. And what are we talking about? We're explicitly talking about storage, memory here, and we're talking about CPU. And what this is this is used to compares designs for efficiency purposes. Hey, this design is going to be more efficient. This is your big O, your analysis, algorithm analysis type of approaches in part. Okay, so in summary, so we should use complexity metrics to guide design decisions. Okay, so the lower the complexity equals lower complexity equals better better maintenance. Okay, and so we can use this to identify disproportionally complex code. So the overly excessively complex code, and to identify it for possible simplification or additional testing. Maybe it's like, okay, sorry, this is bad, but this is just the nature of the beast. Okay, well, if that's the case, well, we better test it more because it's more complex. Any questions? Okay, that concludes for today.